When you read the word reflection, you probably think of looking in a mirror, as all of us have done from time to time. But reflection is the process in which light strikes a surface and bounces back off that surface. Light reflecting from a mirror allows you to see an image of yourself. Do you realize that as you read a book, you are also seeing reflected light? How can the same process cause such different results, though? Is reflection from a printed page the same process as reflection from a mirror, or are they different altogether? Can we find one model of reflection that can explain both situations? Well, the answer is yes. One model can explain both situations. The difference between seeing your own image and seeing a printed page is determined by the surface from which light reflects. The surface of a paper is actually very rough when compared to the extreme smooth surface of a mirror. And if we take a look at these examples, we see what happens to light as it hits a rough surface in comparison to hitting a smooth surface, and we're going to be unpacking this a bit more. The ink on a page also changes the surface. To analyze the process of reflection, which we're going to take a look at in a little bit right here, imagine a mirror surface or a very tiny part of the paper surface that is completely flat. The ray that comes from a light source and strikes the surface we call the incidence or incident ray. The ray that bounces off that surface then is called the reflected ray. To describe the direction of these rays, we need to define certain angles. First, we draw a line that's completely perpendicular to, or makes it an angle of 90 degrees with that surface. And we call that line the normal. And so that is at a complete 90-degree angle to whatever surface the light is bouncing off of, going the complete opposite direction. And the angle between the incident ray, remember that's the ray going to the mirror or to the surface, the angle between that and the normal is called the angle of incidence, which we label fancy science and math terms with the letter I. The angle between the normal line, that perpendicular 90-degree angle line, and the reflected ray is the angle of reflection. And now we threw a lot of terms at you there, but this is how we understand reflection. Reflection is a ray of light that's coming to a surface and bouncing off. But it's a bit more than that. We have to understand how it bounces off, the angles at which it bounces off, and do all of the rays hitting a surface bounce off at the same angle? Do we have a smooth surface or do we have a rough surface? We're going to be unpacking that a little bit, and we're going to discover something that's called the law of reflection. We're going to talk about a plane mirror, one that has just a completely flat surface for a reflecting surface, because that's something that's going to give us a uniform result. And we're going to see how those rays reflect off of a completely flat surface first before we start moving to any changes in that surface. So, as we unpack this, we need to understand that reflection actually comes in what's called the law of reflection. Remember that in our previous slide, we took a look at two different angles. We took a look at the angle of incidence and the angle of reflection. One of those angles was the angle that came from the incident ray, between the incident ray and the normal, that line that's at a complete 90-degree angle to the reflecting surface. And the other one is between the normal and the reflected ray. And when we take a look at these angles, we notice that no matter what, no matter how smooth, no matter how bumpy or rough that surface is, the angle of reflection equals the angle of incidence. In other words, these two values, I and R here, will always be the same, no matter what. And that gives us the law of reflection. It allows us to be able to predict where certain rays or certain lines are going to go when they hit a particular surface. It allows us to be able to figure out mathematically exactly the path that those rays are going to take. For example, if the angle of incidence is 60 degrees, then the angle of reflection has to be 60 degrees. Another important relationship we're going to see is that the incidence ray, the normal line, and the reflected ray all lie within the same plane, and we'll unpack that a little bit more too. So how do reflected rays, though, form an image that we can see in a mirror? Well, this is another interesting way that things work. Now, this is a bit more of a complex diagram here, but if we take a look, we say that we have a light source on the side that is hitting a particular object. In this case, we have a blueberry. And as it hits that object, rays of light bounce off that object all over the place. This is reflection. As some of those rays bounce off, they might bounce into a plane mirror. And those rays, the ones that are already reflected off the blueberry surface, gets reflected once again off this mirror into our eyes. You'll notice for all of these reflections, right? So let's go from the blueberry to the mirror to our eyes. If I were to draw a 90-degree angle line, so completely horizontal in this case, from that mirror, you would see that there's the exact same angle below it as we have above it. And that goes straight into our eyes, which allows us to then see that blueberry. Light's amazing. Light's complex, and it's fantastic. What's crazy about it as well is that when we are seeing the blueberry in the mirror, we're actually seeing an image of a blueberry that goes beyond, or that looks like it appears behind where the actual surface of the mirror is. And this is the way that mirrors work, right? They bounce or they reflect the image of the object so that it doesn't necessarily appear in the spot that we think it might. It allows us to look straight ahead in order to see something that might be behind us. So if we take a look again at this picture, light from a luminous source, the lamp here, shines on an object, the blueberry. This light reflects off all points in the blueberry in all directions, not just to the mirror, in all directions. In the figure, only the rays coming from one point, though, are shown. This one particular point in the very top of the blueberry, they show how that's reflected off up and to the left, up and to the right, and then we have a lot of rays going a little bit more to the right here. All of the rays from the blueberry that strike the mirror reflect according to that law of reflection, and that is that the angle of reflection must equal the angle of incidence. In other words, whatever angle it hits the mirror at is the exact same angle it has to come off at. The rays that reach our eye appear to be coming then from a point behind the mirror. The same process occurs for every point on the blueberry. Your brain knows, though, that light travels in a straight line. Therefore, our brain, again, God wired us so amazingly that it interprets the pattern of light that reaches our eye as an image of a blueberry behind the mirror. Another important feature of images in mirrors we see in this example here of a bird. In this case, the bird is looking at itself in a mirror. But we see all sorts of amazing examples of not only the law of reflection here, but also how an image is created, a virtual image behind the mirror for what that bird is actually seeing. Rays are shown coming from 3 different points on this bird here. So we have points that are coming kind of from its forehead, from its beak, as well as from sort of the lower part of its neck. Notice where the points appear to be coming from behind the mirror as well. Each point appears to be coming from a point that is as far behind the mirror as the real point is in front of the mirror. Also notice that the 3 points are exactly the same distance apart in the image as they are on the object, the bird. These observations explain why the image in a mirror is the same size as the object and appears to be the same distance from the mirror as the object. Now, why are we stressing this so much? Well, this becomes really, really important when we're dealing with a flat or a plane mirror. When we look at an object in a flat or a plane mirror, it creates the image of an object an equal distance away that appears to be behind it. It's not distorted, it's not changed, everything is the same, and that's because everything gets reflected so nicely and uniformly off that flat plane surface. As we're going to take a look in our next video though, we can't say the same thing when we start having curved mirrors. Then that image is not going to be as nice and it's going to start distorting or changing, sometimes in rather odd ways.